Hello, good morning or good afternoon everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Chance Millett-Bangs from Business Review Webinars, and I will be your host. It is our pleasure to have Olympus with us today, who will be discussing advances in ultrasonic and phased array methods of corrosion detection and assessment. Today's guest speaker is Nicholas Bublitz, Global Product Support Specialist. I'd like to welcome you to our webinar platform On24. This webinar is browser-based, so if you disconnect, please click the link you received via email to rejoin the session. All of the icons along the bottom of your screen are the interactive widgets that we have on offer today, so please interact with them all throughout the session. You can ask your questions by using the Q&A widget or by using the questions box, and we will try and get through as many as we can once the presentation has concluded. There are also some URLs and a PDF for you to view in the green resource list, and you may also contact Nicholas directly by using the purple Contact Us widget. Please use the yellow Help widget if you require any more assistance or experience any technical difficulties. So, without further ado, please allow me to welcome Nicholas. Nicholas, over to you.
Thanks, Chance. I just want to second and thank everybody for joining us. I know depending on what time of the world it is, it might be early, late, or middle of the business day. So today we're going to go over, as Chance said, advances in ultrasonic and phased array methods of corrosion detection. A little scope of an agenda for you guys. You can see they're actually different size because we're definitely going to put an emphasis on the different phased array options and some of the benefits of those options. But in order to do that, we first need to kind of set up with Business Review. We do get a very broad audience of different job types, people that understand ultrasound on a user level and some management, and some people that have obviously concerns about corrosion, but maybe not down to the hands-on full ultrasonic perspective. So we're going to do a quick overview, just talk a little bit about corrosion, just so we're kind of can make some distinctions between a few that I'm going to allude to throughout the presentation. Real basic conventional ultrasonic method overview. The bulk of the presentation will be on the phased array options that come from Olympus. Then we'll talk about some kind of specific corrosion testing applications, weld root erosion, a little bit on guided wave, and then some other methodology. So you can see we're going to be cramped on time to try to get everything in a short period of time, but I think we'll have a go and see where we get. So just a brief note on corrosion, depending on what market you're in. Obviously, if you're here this morning, corrosion is a concern. This number coming from a NACE International study, just to put some number on it, estimate that corrosion will cost the U.S. economy alone over $1 trillion in 2015. If you want to see more of that study, the URL will be in the handout, but it just kind of puts a little bit of a idea of the cost of corrosion in society. And the biggest thing about corrosion as a damage mechanism, I think we all know, is it's kind of an equal opportunity damage mechanism. It really affects all the markets in different ways, and especially municipalities that might not require a lot of NDI, but corrosion specifically for water management systems, and definitely the oil and gas industry, but pretty much every industry is subject to being affected by corrosion. Let's just talk a little bit about a few different types of corrosion, just because we will make some distinctions when we talk about different ultrasonic testing methods for different types of corrosion. So when we think a lot about corrosion, I think a lot of people just think about general wall thinning, where we can just have a general slow rate of loss of wall due to corroded material. But there's a lot of other ones that are very concerning for some industries, like preferential weld corrosion, shown here, where the corrosion is actually attacking at or near the weld or heat-affected zone. This one can be really difficult to detect because of the presence of the cap of the weld. Some of the traditional methods might not be so viable, so we'll touch on that one a little bit later. Weld root, flow-accelerated corrosion, microbiological induced corrosion, isolated corrosion pits, and then we kind of lump erosion as well. The erosion damage mechanism can really replicate the same type of damage as corrosion, so most of the testing methods are very similar for things that are actually caused by erosion. And then we have a whole library of related damage mechanisms that can happen in a corrosive environment. And some of these can be the most critical and also the most difficult to characterize and properly assess how severe they are. Things like hydrogen damage, high temperature hydrogen attack or HTHA, wet H2S, laminations, and stress corrosion cracking. The two pictures on the right are just brief illustrations of, on the top, HIC or hydrogen damage in a vessel, and the bottom is actually wet H2S. We'll get to those a little bit more when we actually get into the phased array methods and try to get a little bit better, closer look at them. So we'll do a brief overview for the conventional ultrasonic methods of corrosion detection just as a baseline. Typically the conventional ultrasonic methods for detecting corrosion are on one of two tiers. Kind of on the low end, we do point measurement or data logging with thickness gauges. So that we ultrasonic sensor either with a numeric readout or a waveform readout of the energy along with a reading. These are going to be measuring the thickness only at the point where the sensor is located. A lot of good features for these, a lot of them out there, and it's obviously the easiest way and most inexpensive way to do measurement of corrosion. Doesn't take a lot of training, very easy to use. But there are some concerns about it. For one, you're only taking a point measurement, so it's only as good as the exact point underneath the sensor. So the probability of detecting a pit or some microbiological induced corrosion is generally not as good because you're only looking at one small point on wherever you're measuring, but very good for general wall loss to take a survey or after a pigging or guided wave survey to further assess and get an actual measurement of the actual wall loss. So a very small amount of data density is how we'll refer to it for the rest of the presentation. Somewhat of a record is able to be kept, but that's going to be either just a grid of readings or just a reading or a waveform save maybe. Otherwise it's mostly just a written report. The operator level, so most of these people are on the baseline of doing thickness gauge surveys. They probably might only be qualified level 1 UT thickness gauge versus being a level 1, level 2 shear wave with more experience doing other types of ultrasonic tests. Real big concern in the industry is the use of a gauge without an A-scan. Digital readout type thickness gauges that don't provide a waveform for the operator to confirm it's taking the right measurement or confirm thinning wall versus mid-wall anomaly are usually better suited for the manufacturing industry, where you're just trying to measure thickness and not corrosion or something in service where there could actually be a damage mechanism present. So at a minimum, if we can make any recommendation with thickness gauges, if you're looking for corrosion or you're in the in-service market, is that you at least get a quality thickness gauge with a A-scan or waveform presentation, so it gives the operator a little bit more to go on to make the correct distinction. There's also a big trend to use flaw detectors in lieu of dedicated thickness gauges, or something you might go out and do a shear wave examination with, and then you just put a 0-degree transducer on it and try to take precision or accurate thickness measurements. Within limit. It's not something you can't do, but today's high-quality thickness gauges do have a lot of algorithms, special features, measuring modes that will give you the best results in actually getting a thickness measurement versus most flaw detectors. The last couple of years, a few of the flaw detectors do have some options that are able to be used that do make them closer to the quality of a thickness gauge for thickness readings, but not quite as good as the best of the dedicated thickness gauges. So the real big hard call there, especially as I mentioned before, is if you don't have that waveform, it's really hard to make a distinction between if you're looking at mid-wall defect versus general thinning or some other type of condition. Now my picture here on the right for the second half of the conventional ultrasonic solutions is actually a very modern conventional ultrasound with fully mechanized scanner, but a lot of the points I'm going to make are based on the historical corrosion mapping systems that a lot are still out there in the market and still being used. And those were typically laptop-based or computer-driven, connected to a motor controller that needed to be programmed for the entire area. So you're looking at a reasonable amount of gear, and you're talking about communication between laptop, motor controller, and the scanner. So when we get to the things, we can see that's why some of the negative connotation. But this does have a huge benefit that if you go in and do a motorized conventional ultrasonic test, you do get the benefit of having an encoded, recorded data of an entire area. That data can be archived for the life of the vessel, or it can be compared from scan to scan periodically on a maintenance schedule to see if there is growth in the amount of corrosion that is happening. You do have the ability to analyze all of that data offline. And then, of course, it can be much more rapid, and you get much more data density. So if we're going to do a tank or a vessel of some kind, you get the entire area that you program to scan versus more sampling random points that you would get with a thickness gauge. But there are some concerns with that methodology. If we're only going to use a conventional small sensor in order to make that profitable for the NDT company or even in-house doing your own corrosion surveys, you typically have to move at a very, very, very rapid speed. And in a lot of our industries, we know you walk into a refinery or some kind of processing plant, almost every moving part has a guard around it. Safety is, I think, everybody's main concern as far as corporate ethics and company policies. So to have something screaming at a very high speed in order to make it productive is kind of counterintuitive. Also, the ability to miss data. We'll look at this a little bit further about the typical sensor used in conventional ultrasonic mapping systems, but it's usually a dual crystal, very small, about 0.187 inch. So imagine moving at very high speeds. Our in-service service conditions aren't always the greatest. You have rough walls. You could possibly lose coupling or fall into an actual outside surface rough area or OD corrosion that could cause a data point to actually be missed. If you're actually pre-programming the entire scan and not looking at the data until you're done with it because of the compression and the pixel rate, then there's a good chance that you might have to rescan if you've had enough data drop out. Complicated and lots of gear. That again, those really go back to the old ways now, like shown here with an OmniScan, conventional ultrasonic, and the motor controller. Not really a lot of connections. It's just an encoder in, but when you go back to the dedicated laptop for running an operating system connected to a motor controller, connected to a scanner, there was quite a bit more connections and a lot more complication to the whole process. So what does the industry really need for corrosion monitoring and mapping? Obviously productivity, data quality, high density data quality, low cost, easy to use and learn, portability, reliability, of course, safety, and something that's very versatile. So we'll just go a little bit further into ultrasonic thickness gauging. Obviously, longitudinal sound waves are typically used to do the measurement, and we're typically able to do a thickness measurement from one side. Corrosion thickness gauging specifically, usually we use dual element transducers, and we'll talk about that a little bit further. We used to use a broadband transducer in order to be able to pick up what we're looking for. Anywhere between 0.5 and 10 megahertz. The higher frequency is going to give us a little bit better resolution. Able to go higher than that on some thinner wall or critical applications. And again, with the thickness gauge, we're usually only taking a single point, recording it or reporting it, or we're going to do a grid column area and take a sampling of points to kind of get an assessment of a larger area. And that can be, like I said, either digital or waveform, but best practice at least have an A-scan as shown here so that we can make sure we're understanding where the measurement is being taken and that we're not looking at something that is not actually the corroded back wall but is actually a mid-wall anomaly of some kind. Most of our thickness gauges today and flaw detectors, of course, do have the ability to do single-line B-scans, so we can actually put that dual-element crystal into a small buggy with an encoder and get a rough B-scan or profile down the length of a pipe or the side of a tank, which gives a little bit more audibility and closer to the corrosion mapping system where we have some reviewable data. But really, a thickness gauge is really subject to the point taken in the operator, and there's a few industries right now that are kind of discussing some concern about that. Obviously, if you're given a point to take and that point is difficult to take, it's human nature just to move over a little bit and take another point. So is the sampling really random, and is it really left to the operators? We better have good operators. So there's the general concept. Just a mock-up of dual element on a pipe, looking in that case mainly for internal corrosion. And if we were looking for external corrosion, or we could visibly see external corrosion, we have special small point sonopens and other things that can go down into the pit and measure the remaining wall as well. So basic concept's the same either way. So in general, we find that ultrasonic thickness gauging, the low-end data point taking, is really best for general thinning, spot testing, maybe after a pigging or guided wave screening where where there's subjected corrosion and you want to go in and find a nominal value for that. It's obviously the easiest to employ for high temperatures, because if it is a high temperature situation, we have specialized couplants and you can do a point on, let it cool, go to another spot, take a measurement, which obviously that's much easier than doing a mapping where you have a scanner or a probe in immediate contact with the hot surface at all times. So definitely a very good application if you have high temp applications that you need to measure for corrosion. A few different references there. There'll be a few different references to place on our website for specific parts that you can follow up afterwards as well. So look a little bit further on ultrasonic mapping before we moved on to phased array. We talked about most of this already, but key points, that small footprint means in order to be a really efficient NDI technique, if we want to cover large areas like storage tanks and vessels, we have to move at very high speed. Typically the imaging we're seeing there is a thickness C-scan as shown here. So it is really good that we can get very high resolutions. Typically they're set up for about 1 millimeter by 1 millimeter volumetric resolution. So the chances of being able to detect amounts of corrosion, as long as your scan speed is adequate, not too fast, and we keep coupling to the system, it is a very efficient way to do a high resolution scan. And then because we're programming and we're taking the data automatically, we are really less dependent on the operator. As long as we have a good system that holds the transducer properly to the surface and our coupling delivery system, we're really taking a little bit of the human element out of it. Because it's more volumetric and we're going to scan the entire area, you really do have a better chance of detecting isolated pits. Again, if you are taking a sampling with a thickness gauge, you're only measuring the number of points that you measure. So right next to it, there could be a pit, especially with the microbiological induced corrosion or these through-wall pits that can occur without presence of general wall thinning. This is going to have a much better chance of getting an indication that there's something going on besides a larger area of general wall thinning. So these are definitely obviously best for hard-to-reach areas if you don't have access. Scanners have the ability to be steered and driven up to the top of a tank, that kind of thing. Larger areas, obviously we can't take a ton of thickness gauge readings in an efficient amount of time, so the go-to was conventional ultrasonics with a motorized scanner. And the big benefit there for years, it's been a lower price point than phased array, which we can see that the general trend in the market as we go into phased array here is that things are getting closer and lower cost on the phased array side, and there's some new and exciting things. So one more step on dual element transducers. The reason we tend to use those in a corrosion survey, especially for general wall loss and pitted back walls, is if we just use a conventional ultrasonic 0-degree transducer. We send sound into the part at 0, and because of this irregular surface, it'll often be misdirected, and the transducer will never see the response. By using a dual element transducer, we actually send with the send receiver and receive with the receiver, and these are set at a roof angle designed for varying thicknesses, and that gives us a better chance of hitting an irregular surface and getting the sound back properly to the receiver. You know, thickness gauges and other instrumentation will have algorithms to correct for that small V path as if it was 0, so we actually get a very accurate thickness measurement even by using a slight angle. So usually what we end up getting, besides a better chance of actually hitting and measuring the corrosion, is we get better near-surface resolution as well. By isolating those and put them at a roof angle, we're able to detect things closer to the surface without any hidden signals from the acoustics of firing the transducer. So these are typically used in the best practice with both thickness gauges and the corrosion mapping systems. Look there. So we'll go right into phased array then. So the basic components of a phased array, and it's a real crash course, but basically you have a acquisition unit with software able to program the probes. Some kind of multi-element probe, typically between 16 and 128 elements for most common industrial applications. And all of those are individually wired, which allows us to control the ultrasonics versus being subject to only the mechanic of the transducer. So in this case, in corrosion mapping, since it's at 0 degrees, typically we use what we call linear scans or E-scans. So if we have a multi-element probe here, in this example 16, we actually program that probe to fire multiple 0-degree beams in order to cover a larger area than a single beam. Now the important thing to know, depending on your knowledge of ultrasonics, it's not a paintbrush approach. So for many years in many industries they would use multiple single-element conventional transducers on a multi-channel unit in order to cover larger areas, but at some point you always have a dead zone. You see in the bottom illustration there. Well, no matter how you stack different sensors together, unless you start to phase them and use phased array type approach, you're going to have some dead zones in there, and you're only going to be able to have a certain amount of detection capability. With phased array, you can see all the beams are overlapping, so we don't necessarily have any dead zone whatsoever, and actually we have many overlapping beams as shown here, so we get a high resolution, or what we're going to call high data density amount of data back to that transducer very rapidly. And typically this is the normal approach for detecting corrosion, 0 degree, as it always has been, even when we go to phased array. But phased array does offer the benefit of the flexibility of steering the beam, so we could actually change that to 45, 11, 20 degrees, depending on what we're looking for, and we could have it rastering at that angle at the same time, depending on which probe we're using. Or we could do a multi-angle sweep of beams in order to detect off-axis defects, some of those unique damage mechanisms like stress corrosion crackage and H2S that might be oriented at different places, or any other given angle. And the other big ability is the ability to control the focus depth. Within some limit, within physics, we can actually program the beam to focus at different depths, which can also give us better resolution instead of having to switch out probes or mechanics in order to do that like we would with a conventional probe. So this can give us better resolution and better measurement capabilities. So really, the benefits that we've tried to put into the phased array corrosion mapping market is really taking decades of best practice conventional UT corrosion testing and then improving upon it with the inherent benefits of phased array. So we talked about data density. So if we were going to decide to do a 3-foot by 3-foot area for corrosion testing, or whatever the numbers may be, and we decided with the thickness gauge we would take 1-inch squares, and we'd take a measurement in each one, and generally looking for if there's any sign of general wall loss. We'd call that low density. You're really only taking a few minor points in order to assess or say that this entire area is corrosion free. Now, if you take a high density approach, what we would be doing with phased array is we would take that same area but use multiple beams coming out of the probe, scan the entire area volumetrically at a high resolution, and have a lot of data points and hits. So you can imagine if that same size corrosion cell existed, if it was on the other side, we might be missed, depending on which point we took. In the high density, we might hit it 3, 4, 5, 6 times, depending on all the variables. just a better chance. And obviously, general wall loss, if you had a general trend that is getting large, you might see it over here, but it could still be occurring in between your data points. But isolated pits, micro-obviously increased corrosion, definitely would increase the chance of not being seen. A little illustration on the typical dual element transducer that would be used in a corrosion mapping system with a thickness gauge. You're typically talking average size of about 0.187 inch. So if we scan with that, we're getting a very narrow band of coverage in one shot. Typical phased array approach using one of our average corrosion mapping systems, you're going to get a almost 2.5 inch band of coverage. It's going to vary by the solution. But this is not only important by the data density. It's important because, especially when you're scanning mechanically, with all those overlapping beams, if there's some hitch in the mechanic while it's scanning, or there's some sputter of couplet or water delivery, or there's some small surface issue, data density ensures that there's a much better chance that one of those points is still picking up a sign or existence of corrosion. So a lot of the views we look at are the same, but with phased array views we have a lot of flexibility, and we tend to look at more volumetric views. We still use the C-scan, or the top-down thickness scan, as our baseline, but from there we can start to view side views simultaneously along with the raw A-scan in order to do a really good assessment of what we're looking at. This becomes inherently important when you do have some unique something beyond general wall loss, something like HIC or SEC, or just a mid-wall anomaly that you weren't expecting in your corrosion scan. Another great thing is we can do multiple groups, so we can actually scan at different gain levels. We can look at angle beam scans to catch anything off axis, and we can scan at 0 degrees simultaneously. See an increased POD, increased characterization and sizing due to the views, just a lot more data produced, generally the same speeds, that we can have a lot more tools to properly assess the scan. And then it's very flexible. One probe you can program just on the fly to do basically whatever you want within the physics of ultrasound. So this is typically what we're looking at. We have the C-scan as our map, so we've either done a one-line scan in a straight line, or we maybe did an XY scan over a larger area. And we've defined the unit based on what type of thicknesses that we are concerned with, nominal wall to some other level, and this palette is fully customizable to the application. So in this case, it's sitting from 20 millimeter nominal wall. Everything in dark blue is going to be good wall. We're starting to see some light blue. We're into the 15 millimeter, 14 millimeter range, as we can see on the palette. So this gives us an instant survey of the entire area. And then we can use that and data through it, and we can actually manipulate that very quickly. So if we have the original data acquired, and then we decide the criteria of what we're looking for, it's just a matter of changing those parameters, and then we get another view. So we started at 2 to 20, a very wide range here. Ended up 13 to 20. We wanted to know if anything was even 13 millimeters out, and then we start to get the red, or as this palette's defined, an area of concern. Just another view there. So, one of the important things is when we take just single data points, all you get is a measurement, and you got to try to put all those readings together somehow in your head or analyze it so it's useful for your business. But a lot of the codes and a lot of really concerns about corrosion is not point. It's not one very thin point at one area. A lot of corrosion is more important because of its volumetric extent. So by using the side views and the C-scans, we're able to put cursors on and get those measurements volumetrically. Also very helpful for if we do have something like mid-wall laminations to determine if they have any cracking or sidestep cracking in between them, or any other condition besides the thickness reading that might be useful. These other views really come into a big benefit for that. Just another assessment of it. So again, the top view, C-scan, usually the plan view that we're going to look at to assess things. If we thought this red area, based on our criteria and the setup, was critical, we could click on it and view the data across those two slices where those blue cursors are lying. in each axis, so we get a perspective from the entire volume of the vessel or tank or pipe or whatever we're scanning. So corrosion mapping with phased array. About 4 years ago, Olympus came out with a system called the HydroFORM, which was our real first dedicated foray into corrosion mapping with phased array. And now we have 3 or 4 solutions, so it's one of the reasons we're talking about it today, because it might be a little confusing of what's right for you, any one customer or any one application. So this is just the quick resume of them. We'll go through them a little bit deeper. The HydroFORM is a water-based solution. It is pulse echo ultrasonics, meaning we're just using a single line of phased array elements. We're sending the sound down at 0. It's coming back at 0. It's a reflective response. RexoFORM, very similar except for the fact that it's a hard wedge Rexolite, but again, pulse echo. Single 1D linear phased array probe. The dual linear array, which is one of the newest solutions we're offering, is like the dual crystal UT probe. It actually incorporates a V-path transmit-receive concept versus the pulse echo, but it's also housed on a Rexolite hard wedge. And then we have what we call the RollerFORM, which is a water-filled RSU or roller search unit, kind of the common terminology for the train industry and some other markets. But that is also pulse echo or reflective. So it's really the dual linear array, the only one that is a transmit-receive, common to the V-path conventional transducers we looked at before. Let's talk a little bit more about the HydroFORM. And unique in the one that it is the one that uses water as its coupling method and column. So here we have either put into a small hand cart with an encoder in it, or it could actually be put on a smaller mechanism in order to be put into semi-automated or fully automated scanners. But no matter which, whether it's in the scanner or whether it's in this larger traditional cart, it's going to have a foam gasket that basically seals to the surface. We're going to have a water feed into this, either an automatic water couplant feed or a bug sprayer of some kind that's going to fill this column up with water. And we're basically going to be doing almost like immersion testing while we're scanning. The reason we use water in this application is it offers the best ability to couple to the surface, and especially on rougher in-service, the surface condition even after UT prep might not be perfect. So water offers a great medium for that, and also a pretty good near-surface resolution, which we'll talk about collectively a little bit later. So we're able to change these plates out. So after a period of time, if these plates get worn out, the actual gasket gets worn out from scanning or running over some spatter or something like that. It's toolless design. We just have extras of these in the kit. You slap a new gasket on and you continue to go. We are able to offer that in scanning in the circ direction or down a long seam. The traditional catalog will be designed for 4 inches and above on a circ diameter, and the long seam is really something we assess, and then we decide which diameter of curved plates are needed for it. This is also single or dual axis, so we can scan in a straight line and record the data. We can scan without an encoder, or we could do XY mapping with either a scanner or just manually manipulating the probe. A little bit on the RexoFORM. So again, this is a more common, more simple to the fact that it's very similar to if you were to take a conventional thickness or conventional flaw detector and use a hard wedge to do a measurement on something. And we're using Rexolite, but it's like plexiglass or lucite. It's just a plastic wedge, and basically all the design of it comes into this stainless steel housing that allows one single wedge shape to contour to different diameters. So the real benefit is, compared to just you grabbing a phased array probe and having many different wedges, is that we don't have to actually curve the wedge from 4 inch and above. You buy one mechanism, but the acoustic's going to be very similar. This can also be hand scanned just on time with an encoder. It can be scanner mounted and do XY mapping as well. So again, the main benefit is it's a engineered solution that eliminates as many consumable wedges to fit different curvatures, diameters. And it's also very compact, so this probe that's used with it is a common phased array probe used for weld inspections and other surveys. So if you had a master kit that you like to go out with and you weren't expecting to do corrosion mapping, this would only add about 2 inches in your kit that you could just grab it and be able to do corrosion surveys on the spot, or look for even lamination checks or anything else you might want to do more at 0 degrees versus angle beam. And the other great thing about it is because we're going through the plastic like we do, or the Rexolite like we do, our common phased array probes, there's no limit in steering. If we looked at the HydroFORM, it's really designed for corrosion mapping only in 0 degree. There's some ability to do some beam steering that we talked about before at different angles, but it is limited by the mechanic of the cart you have it in. This being a hard wedge, and our energies from the front to back of this illustration here, we can do a lot of flexible, say -30 to 30 degrees at the same time as 0. For like HIC and SEC and other things, it really opens up the flexibility of the full benefits of phased array beam steering without any limitation. So just the comparison between the HydroFORM and RexoFORM before we go on, because it's really water versus a hard wedge. HydroFORM, optimized coupling on rough surfaces because we use water, and really ideal for 100% coverage circumventional scanning. If you have a lot of scanning to do around pipes, this coupled with a automatic scanner or semi-automatic scanner is a very reliable solution, but it does require water management. We feed that water into this chamber, and that water does come out onto the part, obviously to wet it for the ultrasonics, and some of that's going to leak and go somewhere. So you do have to have a water management system. It's not a great excessive amount of water, but it is something that needs to be managed. And then you have the RexoFORM, huge advantages, pretty affordable, easy to implement. If you have phased array training, you can pick this up in a day and get going. There's nothing really to know extra. It's just a engineered holder that allows the adjustment. Very limited access areas. It does have a very small footprint, so below skirts on different machinery and areas where you might not be able to put a full mapping system, you could complement that program with the scan with this in very tight areas. Very flexible angle steering, so it is a very versatile probe for all different types of damage mechanisms. But it does have that slightly less near surface resolution, which we'll show them all together a little bit later. So taking the best practice of the conventional thickness gauging for corrosion world, we developed a new dual linear array probe. So as mentioned before, this one follows the common methodology of a V-path, or separate send and receive transducers. So everything I've shown up to this point has been 1D linear probes where all of the phased array elements were in a single line and not isolated from each other. The dual linear is actually 2 separate rows of phased array elements. So we have 32 on each side, and then we have an isolation barrier in between so that they can't talk. So one is always going to be dedicated to sending the sound, and one's going to be dedicated to receiving for the sound. So basically the phased array version of the dual crystal probe. See a few other things here. We have some carbide skates in order to preserve the probe, and same adjustment system as the RexoFORM, which allows us to put it on the pipe surface or other curved surface, push down and then lock it into place at the right heights to adhere to different curvatures. Just showing that concept again. So here's the difference between a typical hard wedge and a V-path approach to measuring corrosion. So if we go through a hard wedge, we actually get multiple reflections from the wedge to the surface, between the couplant, and then there's a broadening of the ultrasonic signal by coming out and coming back in too. So typically we might have an interface surface as shown here on the right that's actually masking some level near the near surface, might be a millimeter or 2. With the pitch catch approach, we get a much better near surface resolution set at that V path because we're isolating the send receive. We don't have all these interactions at the surface that cause an interface surface and small dead zone. So we typically say the DLA or dual linear has about a 1 millimeter average near surface resolution, but it can be much better than that. It's depending on the surface condition, the gain, and the actual test application variables. But you can see here there's really no dead zone shown, and then the blue here right below it is an actual defect that we're wanting to see, so it's not masked in any way, because very excellent near-surface resolution. One of the other huge benefits of most of these phased array solutions, and specifically the DLA, is all the programming is done. So the DLA is actually a pretty complicated phased array probe compared to general market probes, in the fact that it's 2 rows of elements and they're pitching and catching to each other. So that can be quite complicated to program. So what we've done for this solution is it's already pre-programmed into the probe. So once you plug it in, all of the setup as far as how the beams, different elements need to talk to each other is already done. So there's really no added complicated process to setting up this pretty impressive probe. And then we've basically provided base setups. So for the carbon steel application anyway, you just choose the setup file that's closest to what you're trying to inspect, and then it's only a matter of moving a few of the acquisition gates to the right position and actually inputting your actual part thickness that you're measuring, and you're ready to go. You can see there's the stabilization system in action a little bit better. So we basically would loosen it up, put it on whatever crude surface we're going to measure, and then lock it down into place. So here's a few acoustic performance examples. So this is a Rexolite block, or lucite, plastic anyway. But it's a very good representation because it has all the types of targets we typically want to be able to detect when we're measuring corrosion. So here we have some flat milled steps. We have some simulated corrosion that was actually laser etched based on looking at actual corrosion profile. We have the normal step wedge that a lot of us doing thickness readings would be familiar with. We have a slope of varying angle, and then we have a small notch in there as well. So the bottom is actually a UT dual transducer put into a small buggy with an encoder and ran down the entire length of the block. We can see on the flat milled parts it does really good. So here we're only using 1 ultrasonic beam. And again, on the stair step we have a pretty good representation of all those reflectors. But there's 2 areas, really. It's the simulated corrosion even, and definitely the slope. We don't really get a great profile of either one of those areas. And then, you know, even though we're using a UT dual, by putting that in an encoder buggy and moving very quickly in order to do a very fast scan of a large area, we're probably missing some of the response back from some of these highly oriented areas. So the PA dual, the DLA that I just was talking about, we basically take it out, we selected the file of the right thickness, changed the material velocity to represent the block here, and move the gates a little bit, and with scanning we get a very even, very good high data, very good quality data of all the type reflectors that we're looking for. One more, whoop, a little too fast. One more example. So this is actually out of a customer's qualification plate. It's 6 millimeter carbon steel. They were tasked with qualifying using this plate, proving their detection capabilities. So this again is using the DLA. This is a 1 millimeter deep pointed pit. Flat bottom holes obviously are great reflectors for ultrasound, but pointed calibration reflectors and actual pits can be a little more challenging, especially when they're very near surface. But same thing, we open it up, grab the DLA, chose the 1 to 13 millimeter steel plate, typed in 6 millimeter, moved our gates a little bit, scanned over the plate, and we immediately are able to detect the sub-millimeter pointed pit very easily with a nice image and resolution of it. So most of these are all compatible with a lot of our scanning options. So you can go out and scrub manually if you want, and just look at the imaging. We can add a simple encoder, like a mini encoder wheel, just to do one line, or manual XY rastering. We have some handheld scanners that can help you do the XY rastering. You can actually scan down encoded strips, push a button, it's going to automatically index over a set value. So you can actually paint a volume, kind of like shown here in the bottom, and get a comprehensive C-scan of a large area. And then we have more dedicated scanners, so link-based scanners for piping systems as well. Those are typically semi-automatic, and the fact that an operator will drive the scanner around the pipe and then use the indexing features to move it over a certain set index and then scan around again until the entire area is scanned. It's a little bit closer look, so this is actually a newer version of the chain scanner. So we have different links for different diameters, obviously, that you would put in depending on what diameter you're inspecting. We have the HydroFORM solution here, so water-based, but a specialized scanner carriage. We would scan all the way around once around the pipe, and then these quick index are actually set to our preset value of how far we want to move on each index. We just click it over to the next one, scan again. So it's a very rapid, very optimized type thing, but you're still having an operator do this scan, with the benefit being there is obviously a lower cost solution with no automation, but you get full encoding in both X and Y axis. Basically the same thing here, but if you weren't doing a pipe or cylinder type, you wouldn't necessarily need the chain link. So this is something that could be employed in a similar XY mapping format on the side of a tank or a vessel or anything you might have to inspect. And then we got automatic scanning. So same basic concept, but we're taking that human element one more step out of it. So this is basically the full mapping system with a phased array unit. Might look something like this, usually just an OmniScan SX, a very small portable phased array system would be required. You'd have the map rover, or a automatic scanner of some kind with one of the solutions, maybe the HydroFORM. Today's power supplies are very small, so it doesn't really add a whole lot of bulk to the kit. This one's actually unique, then it's almost like an Xbox. It's very easy remote control touchscreen data input as far as the scan parameters. So we don't have any complicated motor control to program the area you want to scan. You can just input it here. The only communication from the scanner back to the OmniScan is just a single encoder cable. And then here's shown some automatic water feed to regulate the flow of coupling as well. One being just a normal water feed, the other one being having the ability to suck some of that coupling back or recuperate some of that coupling that's going out on the part. So obviously these become a huge benefit for a few reasons. Obviously if it's a hard to reach access area, a steerable, drivable, or some way to get to the area of inspection, especially if you can't scaffold and get a person up there to take more manual readings. But it also has much better data quality when we automate. So if we can control the exact speed it's always moving, we can control all those type of things, we're going to get a much better data quality as well. So why is this a game changer? Well, if you look at the historical mapping systems, and many of them, some are out there, some of them were quite complicated. Took lots of pieces of gear, possibly lots of communication. So you have an operating system on a computer, you have the connection to the motor controller, then you have the connection back to the unit. Error communication problems can occur. Just so you run at unsafe speeds, might not know that you've missed data until after the scan because it's hard to view large area data moving at that speed on the fly. And then, typically a conventional ultrasonic mapping system, that's what it does. It's not designed to do a whole range of other ultrasonic tests. So if we look at the phased array approach, we take the lower end encoding capable SX, couple it with a scanner, and we immediately have a very high quality corrosion mapping system that's also very portable. No real programming. Again, the only link back is the scanner needs an input back to the encoders of the OmniScan. Otherwise, the programming of the scanner is completely done by the remote. Higher POD, as we mentioned, higher data quality. And we can achieve that at a much slower, safer speed. Because we're covering 12 times as much on a single width, we don't need to move at the same speed as conventional ultrasonics. And at that slower speed that we can often scan, we can actually spot if we're having troubles with the system or if there's some loss of data, and we can immediately go back and get it right away. But then the biggest one for me is that it does offer that flexibility. I mean, this is the same system you can be using for weld inspection looking for cracking or component testing, and there's really no distinction. It's not a dedicated corrosion mapping system. It's a full flexible phased array for all different types of ultrasonic applications. So we did a few tests between our OmniScan on the UT side and our OmniScan on the phased array side, and we basically mimicked the setup on both. And on average, typical application, setting them up for the same pipe, we see a data acquisition rate increase of 50 to 1, even though we typically can move at a slower speed with the phased array. One last one to talk about is a little bit unique, but a lot of people like it because of its form factor, and that's the RollerFORM. So this was actually designed for composite testing and thin skin or smooth skin aerospace applications, but it can be used in the more industrial metals market as well. So basically, we have a phased array transducer inside of a water-filled search unit here, an index button, and some other controls. But basically, we'd scan down in a straight line, use the index button to go over a fixed distance, and be able to paint a complete XY map. So very interesting. A lot of people like the form factor and the ease of use. Again, but it was designed, its best performance is in composite inspection, thinner materials, but also smoother materials. But it can be used for other applications. It is very good for axial scanning, so down to 4 inch, especially if you know the presence of corrosion is always in the bottom of your pipe, or maybe it's between 3 and 8 o'clock. You want to test the sides and the bottom. It could feasibly be used very readily for that. It's very quick and easy to get started. On a very smooth surface, it doesn't take much wettability. If you do have a very rough surface, it might take a little bit more water. But basically, the coupling is done just by putting coupling on top of the material, and it goes through the water, through the membrane, into the surface. But it does have a limitation. The near surface resolution is not as good as any of the others. So a general baseline, if you just want to detect the areas of corrosion, then go back and measure them again with dual element, or you just want a general idea of the amount of corrosion, not looking for a very, very thin wall, could be an option. So there's a kind of a resume based on near surface resolution. We talk about near surface resolution is not having a dead zone, the ability to resolve reflectors very near the surface that we're inspecting from. So obviously, if you want to be able to detect something that's could be very critical, something within 1 millimeter of the surface opposite your testing, the dual linear array is going to have the best capability of doing that. So a little bit another comparison table. I won't go through it all. I'll just point out a few quick things. So scan speed, typically for all these, we baseline them with a resolution of 1 millimeter by 1 millimeter. So in that, we're talking about the scan axis and the index axis. So when you get the data back, you're able to look at every millimeter in both directions, and that's your resolution scale. Typically, the DLA, the way it's programmed and the way it works, does have the ability to usually scan at a much rapid speed. So you're looking at 100 millimeters per second for the Hydro Rexo is very typical, and up to 300 is pretty typical for the DLA corrosion probe. Most of them are compatible with most of the scanner options as well. You just got to have the right configuration. Let's look at analysis really quick. That can be done on board. We have a simple program that looks like the OmniScan called OmniPC. It can be done there as well. We have some more advanced analysis options in our TomoView analysis software. And then we have the ability just to Excel exchange. So a lot of people that are doing corrosion mapping programs, you're already taking this data out into, out into Excel. You might want to have to report it to other people that might not understand ultrasound, or you might want to run that data, do R strength or fit for purpose calculations, and look at that in different ways. We basically, with export of data, you can just manipulate it however you want and have your Excel spreadsheets up to run your calculations or make pretty graphs for boardroom meetings or whatever you need to do. Just gives you the raw text data, which then is obviously can be converted to displays. To go a little behind in time, so I'm going to move a little fast to the calibration and performance. One thing is verifying, obviously, resolution and performance. So this is actually a plate with different flat bottom holes of different resolution or different sizes milled into it. So there we did the full scan of the entire plate, and we can see the different resolution holes from, I think it's 0.01 up to 0.05 diameter flat bottom holes at different depths. Another resolution block here, 0.1 to 750. Gives us a good confidence that the system is set up properly and we can get the measurement and depth value precision that we're looking for. General thickness gauge too, thickness step that we might use to calibrate a thickness gauge. Very easy to run that over the DLA probe, and you can show the linearity between your whole thickness scale that you're trying to measure very easily and save that file for auditability purposes. So calibrations come into question because with phased array we obviously have multiple beams we need to calibrate. But really the wizards and 0-degree calibrations are pretty easy because basically all the beams are pretty much the same. Just a little variability in the surface they're sitting on. But simply if you want to do a full equalization of the beams, it's a one-step process, a little wizard that sees all the beams and then does a correction. So it's really almost as fast to do a 64 ultrasonic beams as it is to do one conventional beam. All that's saved into the file. We do have the ability to do TCG or attenuation compensation, velocity, wedge delay corrections, and compensations as well. A few unique applications that are kind of outside of the 0-degree corrosion we've been talking about. So flange phase crevice corrosion, typically with these, it'll happen right between the gasket or anything, and that's either radiography or disassembly and visually test them. We find that phased array, just make some calibration targets, you can get a pretty good quantification of the amount of corrosion. Since it is sitting under pressure and with that gasket present in a lot of cases, it is a quantitative. You can usually see the amount of corrosion, but you're going to say it's classified as ABC or 10, 20, 30. You're probably still going to take apart the ones that you do see a good amount of corrosion. But it is extremely helpful to avoid the radiography and then to kind of prioritize your NDI, especially during shutdowns and turnarounds. You can take them from the bolts or from the lip, depending on the configuration of the flange face. It's more illustrative of what the ultrasound is doing there. And there are some third-party solutions out there that actually can scan from the top of the flange as well. Custom solutions, we always take those on as well. We're able to do things like curved large probes to cover certain areas of a pipe. If you know there's one area of the pipe because of the product that flows through it, we've done some custom solutions that will fit that need for customers. We do offer feasibility studies, application studies, and a lot of our technical sales staff as well can look at applications when they come to visit you. So the summary of the benefits, we went through most of these, but just to summarize, again, I can't emphasize data point density enough. Imaging, especially for non-general wall thinning, but some of the unique damage mechanisms and be able to catch those, the imaging is great. Very large coverage with the phased array probe. The ability to move at slower speeds with large acquisition, which means data recovery and also safety. Very programmable and flexible. The angles, the groups, the depth focus really gives us a good chance at assessing corrosion correctly. Very portable, battery-powered and small with limited communications. Only the minimum phased array is really needed for the base 1664 0-degree mapping. What that means, basically basic phased array training. If you get into weld inspection with phased array, it's a little more involved to learn the process and proper setups. But being at 0-degree, you can take a guy that understands ultrasound to the phased array program very quickly. No PC is really needed unless you want to do some post-offsite analysis offside the instrument. You can do it just directly on the unit. Typical area resolution there, 1 by 1, and also a 1 millimeter near surface resolution with the DLA. And then that's a very flexible unit when you use a phased array unit because that same unit can basically be used in all kinds of ultrasonic tests from automatic weld testing to component testing. Usually have the ability to do time of flight diffraction as well. So it's a very beneficial, flexible system. So at the end of the presentation is some things I knew I probably wouldn't have time for, but you'll get the handout, you grab the resource. There's some app notes depending on what kind of corrosion you're interested in. There are some guidance to some other webinars, some more in-depth if you're more of the operator NDT guy and want to learn about these tools a little bit more on a technical level. We can point you to all of those. So you get that and you're able to check on some of those links. So at this point, I will turn it back over to Chance. I'm not sure if we have time for a question or two or not, but we'll find out. Okay, so it looks like we had a disconnect, so I am going to go ahead and answer one quick question, and then I think we're at our time allotment. So we had one, can it be used on stainless steel? Yes, it's a good question. I mean, stainless steel varies a lot by the grades and whether it's austenitic or not, and then actually the process it goes through can change that as well. The answer is yes, and we do a lot of acoustics on that. Usually we design and baseline them for carbon steel so that we can use something homogeneous to be able to give out numbers like 2 to 80 millimeters in carbon steel, dead zone of X. But stainless steel and all the other variable materials are possible. It's just more of a, we'd like to do some acoustic tests to make sure. So at this time, I think that's all we have in for questions. So what we'll do is we'll end it there. There are quite a few questions, about 24, 25. So anybody that asked a question today, we'll go ahead and answer those via email in the next couple days. Because it's Thursday here, it might be by Monday, Tuesday next week, but we'll get to them all. So at this time, I'll turn it back over to Chance.
Excellent, thank you, Nicholas. So that just leaves me to thank Nicholas for what was a fantastic presentation, and also a big thank you to Olympus for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. Please continue to ask your questions and interact with the widgets as the on-demand version remains fully interactive. We look forward to sharing further webinars with you, so please do keep an eye out on our website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.